let's go into it so that we can get an understanding or get a grasp of what's going on when an aeroplane flies. Now, I want to show you some footage here. This is a Boeing 747. We watch these huge machines take off and land regularly these days. We ride in them ourselves. But I think we've grown too accustomed to that, haven't we, without thinking about what's going on. So firstly, can you tell me how much does that 747 that we're looking at, how much does that weigh?
This particular model, Garry, weighs in at 355 tonnes.
355 tonnes. Now, what's going on here, John? How is it possible for something that heavy to seem to effortlessly leave the ground?
Well, basically, if you've got something that weighs 355 tonnes, the wings on the aircraft have got to be able to generate 355 tonnes of lift force. In fact, probably just a little bit more. Now, we looked at the 747 getting airborne. If we compare that to a Swan getting airborne, they look very different, but they're just as elegant as each other. The principles are the same, though. Just the way of doing it is slightly different. But the wings are effectively the same shape, and it's what we call an airfoil section or an aerofoil section. And what happens here is that you actually accelerate the air over the wing, and that generates the lift. And that's what we're going to be sort of looking at during this conversation.
Okay, so it's all about the air moving over that aerofoil, moving over that wing, top and bottom, and that's what's creating the lift.
That's correct.
All right, well, let's talk about how we got there. You know, we've dreamed of flying since we've been able to look at birds, haven't we?
Indeed. Angels taking the good souls to heaven and stuff like that, which is the stuff of legend. And talking of legend, then it took a more practical approach in Greek mythology with Icarus, of course, who tried to make his wings out of wax, and he flew too close to the sun and the wax melted and he fell into the sea. And there is an awful lot of that mythology in the background to what man has wanted to do to get airborne.
So why can't we fly just by flapping our arms?
Well, basically men's arms are not strong or flexible enough to be able to generate enough lift or to carry a wing big enough to carry his weight. And that's the limitation.
Okay.
If you look at birds, they're very light, and they've evolved over millions of years to be able to fly and carry the weight.
They are, but as we said earlier, the 747 is 350 tonnes, so it is possible to get enough lift to lift a very heavy body. It's just not with human arms that we can't do that.
Absolutely.
Yeah.
And, we talk about the mythology, but it didn't stop man from trying.
And I think there have been a lot of accidents and a lot of failed attempts, haven't there? You know, people, let's face it, have been tenacious, haven't they? They have tried and tried again to make this happen. So if we go right back as far as we can, where do you reckon man's journey into flight began?
Well, I think the earliest recorded flying object that we have is the quintessential Australian boomerang. And the earliest dating of those is 23,000 years ago. The interesting thing about it was that they were actually shaped, so they did have an airfoil shape. It took a few millennia for man to realize that you just didn't use that as a weapon. You'd be able to use it as a vehicle to fly. And of course the thing did come back to the launcher, or the person who launched it, which made it a very useful weapon.
Very clever. So I guess the next step that we could look at in history is a kite. Would that be right? Describe the kite and what's going on there.
Yes, a kite is basically an airfoil section. I mean, many people would consider that they're not, but it's a tethered device which has a shape, an airfoil shape, so that's what generates the lift.
All right.
And if you remember when you were a youngster running along the beach or over a hill or something, pulling a kite behind you to generate enough lift on the surface to make the thing fly. And they date back to about 2,000 years ago in Chinese legend, not legend, but in Chinese fact.
History, yeah.
But the Chinese didn't really twig to using it as a weapon or advancing its design very much.
So to be clear, it's not the wind blowing this kite into the air, it is actually flying. The air moving over the kite is causing lift.
That's correct.
And it's flying.
Yes.
Okay. All right, well, let's jump ahead then a little further. We're going to be about 500 years ago from now. We've got Leonardo da Vinci. Now, I always thought Leonardo da Vinci was a sculptor and a painter. What was his involvement with the development of an understanding of flight?
Well, he was not only an artist and a painter, but he was a bit of an engineering genius. And he was fascinated throughout his life with the idea of flight. And included in his works is actually a theoretical book on how birds fly, called the Codex of the Flight of Birds. And as well as actually writing that book, he described various flying machines theoretically, but he didn't actually go into practical application of it. But he had a thing called an ornithopter, which flapped its wings, and he even forecast a helical rotor of an early helicopter.
Well, I think the next name that probably needs to be mentioned is Bernoulli, Bernard Bernoulli. What did he do?
He was a Swiss mathematician, and he came up with the principle of that an increase in the speed of a fluid, and we can consider air a fluid in this line of argument, occurs simultaneous with a decrease in its static pressure. And if I understand it correctly, he was inspired by the movement of water, and that's what led him to the principle. And the principle was actually proved by practical application.
Air speeds up, pressure what, goes down?
Yes.
Okay. So on top of the wing, if the air is faster than below the wing, the pressure above is lower. Is that what he...
That's correct.
Okay. So this then, I guess, was the beginning of the concept. Who took that idea and started to begin to create wings that actually did lift us?
Well, we have to go ahead really to about another 200 years. And by the late 1800s, man-carrying gliders had been proved to be feasible. A number of records of it are very difficult to find the authenticity of. But the German inventor, Otto Lilienthal, from about 1891, started to produce man-carrying gliders, and he demonstrated them quite regularly in Berlin. But the most problematic thing for him was control. He didn't have a method of controlling them very well, to the point that he was flying one in 1896, and it led to his death. So, and controllability was one of the early problems that they had. It was Sir George Cayley who really was the father of aviation, and he understood very quickly how airfoils work, and not just from a basic principle of engineering, but from practical experience. He did a lot of not wind tunnel testing, but he had a rig which could actually be rotated so that he could check the amount of lift. Now, that, funnily enough, was coincidental with a lot of the work that Lilienthal did, because he actually produced a table of airfoils that he had tested and their various different shapes. So, these things don't just happen in isolation. And so Sir George Cayley was able to capitalize on a lot of the work that had been done before. But he went ahead and he experimented with gliders, and that led him to the conclusion about the principle of lift, or the forces that are involved in making an aircraft fly. And that is that you have to produce lift to counteract the weight, and you have to produce thrust to make the thing go forward fast enough to be able to generate lift. So and with that, it produces drag.
It was Cayley who really first clarified that.
Indeed it was.
Yeah.
And he not only clarified it, but he made a glider that he made a series of gliders, but he was the first to make a glider that was man-carrying and controllable.
Tell us about his poor coachman.
Yes, well, this, of course, is again the stuff of legend. He built this glider, and he put his unfortunate coachman, and presumably the fellow had to volunteer for it, and flew him across a valley. and the machine was actually controllable. There's a copy of it in the Smithsonian, in fact. But he did realise, or Sir George Cayley realised very quickly, that he didn't have sufficient power to be able to have a sustainable flight. And he predicted that sustainable controlled flight would only become a reality when an engine light enough and powerful enough would be available to produce the thrust.
So I suppose Cayley was inspired by a bird's wing in that regard.
Yes.
Let's move on then to about 50 years later to the Wright brothers. Now, who were these brothers who many people now have heard about? They had a bicycle shop, didn't they? I think they were even inventors of bicycles, and they must have known about George Cayley's work.
Yes, there were a couple of brothers who dedicated themselves to learning about flying. And their bicycle shop was just a means for them to produce enough money, I think, to be able to take this. It wasn't just a hobby. I mean, they were totally dedicated to it, and they'd done an awful lot of study. And they attributed their success in large measure to Cayley. Now, like all these things, the fact that they produced the first flyable aeroplane was not just an accident. It wasn't a light bulb moment. It was a lot of hard work. They had a wind tunnel, for example. Did they? And they experimented with various different shapes of airfoil until they came up with what was their workable Wright flyer. And it was a fairly clumsy machine, but nevertheless, it flew. And that was on the 17th of December, 1903, on the coast of North Carolina in the United States.
At Kitty Hawk.
At Kitty Hawk. Because it was so windy, that's why they actually flew it. Now, the first flight, of course, was less than the wingspan of our 747. It was only 55 metres. And the 747, of course, is 68 metres. Right. But that was the first flight. And on that first day, they actually made 4 flights. And within a very short time, they'd established that it was a practical proposition. Their machine was a practical proposition. It wasn't just a gimmick. And if you look at the history, there was an awful lot going on at that time. Langley was a famous inventor in America as well, who was trying to get to fly about the same time. He was notably unsuccessful. And the Wright brothers then, of course, went ahead and achieved what they achieved. And I think there are 2 key words here, aren't there, for their contribution, and that was sustained and controllable. Yes. Those are 2 key words, aren't they? Yep. Just explain those. Well, first of all, the thing had to be able to stay airborne under its own power. And the reason that they were very successful was because they produced their own engine. Internal combustion engines had been known, but to have one that was light enough to fly, they had to design themselves, and they had a mechanic who put it all together for them. And then, of course, they also had to experiment with propellers. This machine had 2 propellers. When we talk about sustainable, that means you've got to be able to have the power to be able to produce the thrust on Cayley's principle. But then, having got it airborne, of course, you've got to be able to control it. And in 3 axes, you've got to be able to control it in pitch, so that it will go up and down, and in bank and yaw. The way that they did it in their machine was actually quite complex, because they lay it down on a cradle, and the cradle actually was the part of the machine that actually made the thing bank and turn. And they understood very quickly, or from their experiments, that if you just turned an aircraft using a rudder, all it does is yaw the aircraft. So they had to have a mechanism where the change in lift on the airfoil sections was done in combination with the rudder, so it was a balanced situation. The way that they actually made the aircraft bank was to wing warp, as we talked about before. So they had a series of cables, and they actually bent the wing, because the wing was made of very flexible materials. It was wood and linen, basically, that was stretched and doped. Now, you've used 3 key words again there.
pitch, yaw, and I think you say bank or roll. Roll's another word, isn't it?
Yep.
So pitch, yaw, and roll, and they understood the relationship between those three, didn't they?
They did indeed. Yep.
And I think hang gliders today use that same process of shifting their body weight to adjust the direction of flight.
They do indeed. And of course, that's where what Lilienthal did before he became unstuck. So.
Yes. It's just amazing to trace the development, isn't it? And to see over the years how one has built upon what's gone before and taken it further. So we're in the 20th century. We've talked about the Wright brothers, and we've seen that it all seems to be happening now. We've got the potential for sustainable, controllable flight, heavier than air machines that might actually make flight a realistic possibility. We come to 1914, and unfortunately the world is plunged into war. What impact did the coming of a world war have on the development of flying machines?
When the World War I broke out, basically the aircraft was used for observation.
Okay.
It replaced the balloon, if you like, because if you could view where the enemy was putting their trenches and moving their troops, then it was a very useful mechanism for that. Quite early on in the piece, observation machines were passing each other away to look at each other's front lines, and of course they started to shoot each other's with revolvers and rifles, and then fitting machine guns to the aircraft.
And did this life and death struggle that it became advance our knowledge and our technology of flight?
Oh yes, very quickly. Just going back to the Wright Flyer, that was a very ungainly machine, and its manoeuvrability was limited. And quite quickly, the biplane emerged from those designs, apart from Blériot, of course.
Now, you mentioned Blériot. What was his contribution?
Well, he was the first man to fly across the English Channel. French aviator inventor, but surprisingly with a monoplane. And he surprised everybody as well, because he arrived on the other side of the English Channel, I think, quite unannounced.
Nobody expected to see him ever again. Well, explain to us the difference between, biplane means two wings, monoplane means one wing. What's the advantage of going, why do we no longer rely on biplanes?
Well, initially, when they started to fly the aircraft very fast, they were using biplanes, but biplanes very quickly showed themselves to be limited, and monoplanes then took over.
So essentially it was the quest for speed that led to the monoplane winning out.
Yes. And because there were also limitations, if you look at a biplane, it produces a lot of drag as well, because you've got bracing wires, and there was quite a lot of what we call interference drag between the upper and the lower wings.
Right.
So the forward speed of the aircraft was limited by the amount of drag you were producing.
Okay. So let's just recap for a second here. We're talking about 20,000 plus years of human experimentation and developing of knowledge about flight. We talked about boomerangs, we've talked about kites and so on, but it always comes back to this technical term aerofoil or airfoil, and the shape of this thing moving through air or having air move over it. That is essential to creating lift. And we've been able to observe birds, we've been able to observe insects doing this by flapping wings, and we've had to come up with a solution that didn't involve flapping the wing, because that's just technically too difficult to do, I suppose, for us in terms of a machine. So we've gained this knowledge about the way wings behave, and we've experimented with increasing sustainability and increasing controllability of the machines that we're trying to fly in. We haven't quite made it yet to the heavy jets that we started out talking about, like that 350-ton 747 taking off, but we can see that we're getting there. We can see we're making those developments. After the First World War, you've mentioned increasing speed, crossing oceans. This must have been something. Across an ocean in the air.
Yes, by the end of World War I, the arrival of the big bombers came, because you needed to carry more and more munitions to be able to make use of that air superiority. And that's how we ended up with the big bombers. End of World War One, what do you do with all these aircraft? And it had already been proved that you could go a long way with them. And so it was axiomatic that people would want to start using them as passenger carrying vehicles. Now we're looking at it as being a possible quicker means of getting around than by steamship, which was the traditional way before.
Right, and including the fact that heavier and heavier loads could now be carried through the air quickly. I think at the same time as all of this experimentation is happening, trans-ocean flights, heavier and bigger aircraft, we've got Qantas being formed, haven't we?
Yes. Funnily enough, Qantas and KLM in 1920 were the first two big airlines to be formed.
Royal Dutch Airways, yeah, yes. KLM.
Just on that note, aircraft were still very unreliable, and engines were very unreliable. And people who actually undertook air travel were considered to be very brave.
Yes.
They were, of course.
Yes.
And flying these quite fragile machines in heavy weather conditions was an adventure in itself.
Very dangerous.
Dangerous, yeah.
Yes. Nothing like today, where we have managed to make them the safest form of travel that there is.
Yep.
Yeah. Let's talk about through the Second World War then. Unfortunately, we're back at war in 1939. We now have the predominance of the monoplane. We have much more reliable piston-driven engines, but this is the coming of the jets too, isn't it? And a whole different kind of challenge to allow an aircraft to cope with the power of the jet engine.
By the end of World War II, the engines had actually reached, piston engines had reached probably the end of their development. You were getting about as much power to weight as you could get out of them. And, you know, if you look at the early Spitfire engines, they were about 1,200 horsepower. And by the end of the war, the big radial engines were capable of producing 3,700 horsepower. But there were penalties, and they were complicated pieces of machinery, beautifully built, superbly engineered. But the jet engine came along, and the jet engine was a very much simpler way of pushing an aircraft through the air. You didn't have all those big pistons and the requirements of cooling and so on that you have with a piston engine. Basically, you have a compressor, a combustion chamber and a turbine, and it's a continuous flow engine.
So why then did wings begin to be swept back?
Well, with the limitation of straight wings, we mentioned that air behaves much like water, like you can consider it to be a fluid, until you get to near the speed of sound.
Which is what, about 700 miles an hour, roughly?
Yes. Yeah. And what happens then is that the air going over the wing produces a shock wave. Right? Because you're accelerating over the top of the wing, the air is at its fastest at the highest point on the wing, or the most curvature on the wing. Now, when you get towards the speed of sound, you start to produce a shock wave. And what that does is it causes a massive separation of the air behind the shock wave, which then causes control problems. Okay. And it can blank off the tailplane. And they had, in World War II, a lot of fighters would go into very steep dives from which they couldn't recover. And in part that was due to this breakaway of the airflow, and in part because the tailplanes and the pilot with manual controls simply didn't have enough power to be able to pull the aircraft out of a steep dive. And it was the theory of actually sweeping a wing to delay the effects of that transonic zone actually was tabled at a conference in about 1936 by a German physicist or aerodynamicist.
Of course, now we're very familiar with that shape, even to the point of supersonic flight, where we have the delta wing and so on. I don't know that we need to go into all of that today, but you've described the principle, which is that when you reach that kind of speed, you have to alter the shape of the wing to cope with the movement of the air.
Yes, and also not only did you change the angle at which that's where the swept wing came in, but also the thickness of the wing was another aspect And there were huge engineering problems to be overcome to enable a wing to be able to build to be able to sustain the weights and the loads that they had
Be
to
strong
carry.
enough.
Yeah. Strong enough is a much better way of describing it.
Well, let's come back to where we started. I mean, we're not pretending that we've covered everything there is to say about wings. We haven't talked about helicopters much. We haven't talked much about supersonic flight. But let's get back to our 747 that we were looking at the start. Can you talk us through, okay, so we're going to watch this 747 as it accelerates down the runway, and we're going to see it take off. Tell us again, what are these four forces that are acting on this aircraft as it's picking up speed?
Okay, well, as it starts to move forward, the wings then start to produce lift. Let's just work from the premise that you've got flaps at the back of the wing, which are droop down, and they change the actual angle of attack of the wing, or the shape of the wing. Not the angle of attack, just the shape.
The shape.
Now, the aircraft accelerates along the runway, and you can see from this diagram that as it accelerates, it starts to produce lift. There's much more thrust than there is drag, and the faster you go, the more drag you produce. But clearly, to make the thing work, you've got to produce an excess of thrust. Now, to make the aircraft actually get airborne, we've got to add another factor, and that is called the angle of attack. And if we look at what happens next, is that the pilot pulls back on the stick, and that increases the angle at which the wing meets the air, and it produces a very dramatic increase in the amount of lift. And that's where the aircraft lifts off the ground. And it's that increase in the angle of attack that is what produces the excess lift that enables the aircraft to get airborne.
Okay, so we've got lift, we've got weight, and we've got thrust, and we've got drag. And in this particular balance, we have the capability for a 355-ton aircraft to lift off and fly in a sustainable and controllable way. We did talk about flaps briefly. We've talked briefly about a number of issues that I think we should come back to. For example, I'd love you to explain why modern jetliners fly at the altitude they do. What does that mean about the density of the air and how that affects the wing and all of those kinds of things? And if you're sitting in an aircraft and you're watching the wing as you land, you see the flaps come down just before landing and so on. So we could go into all of that. But I think what we could say for now, thank you, John, is that we have summarised the notion of lift, which is what gives us the capacity to fly in these heavier than air machines. And it's a marvellous, marvellous thing. Thank you, John.
You're welcome. Yep.